Helicopter Flying Handbook 2.2 Aerodynamics of Flight. Parasite drag is another form of drag that is ever present when the helicopter is in motion through the air. This type of drag escalates with airspeed and is associated with non-lifting components of the helicopter, including the cabin, rotor mast, tail, and landing gear. Any disruptions in the airstream, such as openings for engine cooling, contribute to additional parasite drag. Notably, parasite drag is a major contributor to drag at higher airspeeds, rising rapidly with increasing velocity and varying with the square of the speed. Doubling the airspeed results in a fourfold increase in parasite drag. Understanding total drag involves considering all three drag forces: induced drag, parasite drag, and profile drag. As airspeed increases, parasite drag rises, while induced drag tends to decrease. Profile drag, which remains relatively constant throughout the speed range with a slight uptick at higher speeds, is also part of the equation. The combination of these forces results in a total drag curve, with the lowest point representing the airspeed where drag is minimized. This point, known as DMAX, signifies the optimal lift-to-drag ratio and holds significance in determining helicopter performance. Helicopters achieve flight through the manipulation of aerodynamic forces generated by airfoils. An airfoil, defined as any surface producing more lift than drag when appropriately angled in the air, plays a pivotal role in the flight dynamics of helicopters. While commonly associated with lift production, airfoils, such as rotor blades both main and tail, also serve functions like stability, control, and thrust. The careful design of airfoils extends to various parts of the helicopter, including the fuselage components like the vertical and horizontal stabilizers, each tailored to meet specific flight characteristics. Key terminologies associated with airfoils, such as blade span, chord line, mean camber line, leading edge, and trailing edge, elucidate the intricacies of their design and function. Understanding factors like flight path velocity, relative wind, induced flow, and angles of attack or AOA is essential for comprehending the nuances of how airfoils contribute to the complexities of helicopter flight. The interaction of these aerodynamic principles defines the flight envelope and performance of helicopters under varying conditions. Airfoil types play a crucial role in the aerodynamic performance of helicopter rotor blades. Symmetrical airfoils exhibit identical upper and lower surfaces, generating no lift at zero angle of attack. Many light helicopters integrate symmetrical airfoils in their main rotor blades. In contrast, nonsymmetrical airfoils have distinct upper and lower surfaces, with a greater curvature above the chord line. This design allows for lift production at zero angles of attack, offering advantages such as increased lift at a given angles of attack, improved lift-to-drag ratio, and better stall characteristics. However, non-symmetrical airfoils also present challenges, including center of pressure travel and higher production costs. Blade twist is incorporated into rotor blade design to address lift differentials caused by varying rotational relative wind values along the blade. This twist helps distribute lifting force evenly and reduces internal blade stress. The twist results in higher pitch angles at the root, where velocity is low, and lower pitch angles near the tip, where velocity is higher. This design enhances induced air velocity and blade loading near the inboard section of the blade. Additionally, specific rotor blade and hub definitions are crucial for understanding the dynamics of helicopter rotors. The hub serves as the attaching point for the root of the blade and the axis about which the blades rotate. The tip represents the farthest outboard section of the rotor blade, while the root is the inner end that attaches to the hub. Twist, in this context, refers to the change in blade incidence from the root to the outer blade. The angular and radial positions of the main rotor blades are measured from the helicopter's longitudinal axis, offering insights into their orientation and distance from the hub. The understanding of relative wind is fundamental in aerodynamics and its application to flight. Relative wind refers to the airflow relative to an airfoil, which is generated when the airfoil moves through the air. This movement creates relative wind that flows parallel but in the opposite direction to the airfoil's motion. The relative wind has horizontal and vertical components, influenced by both the rotation of the blades and any vertical movement of the helicopter. Rotational relative wind, also known as tip path plane, is produced by the rotation of rotor blades around the mast. This wind flows opposite to the physical flight path of the airfoil, striking the blade at a 90 degrees angle to the leading edge and changing direction continuously during rotation. The velocity of rotational relative wind is highest at the blade tips and decreases uniformly to zero at the axis of rotation. The resultant relative wind, which is present during a hover, is a combination of rotational relative wind modified by induced flow. It is inclined downward at some angle and opposite to the effective flight path of the airfoil. The resultant relative wind serves as the reference plane for lift, drag, and total aerodynamic force vectors on the airfoil. When the helicopter has horizontal motion, airspeed further modifies the resultant relative wind, with the airspeed component added or subtracted based on whether the blade is advancing or retreating. Induced flow, or downwash, is produced when the rotor disc induces a downward flow of air through the rotor blades. This downward flow is most pronounced at a hover under no wind conditions. The blades induce a column of descending air, reducing the angle of attack due to downwash. In ground effect or IGE, hovering near the ground increases rotor efficiency by interfering with the airflow, allowing for a more horizontal relative wind, a more vertical lift vector, and reduced induced drag. Out of ground effect or OGE occurs when the helicopter is above the IGE altitude. Above this altitude, induced flow velocity increases, resulting in a decrease in angles of attack and lift. This increase in induced flow velocity and pitch angle leads to more drag, requiring additional power to hover OGE. Understanding these aerodynamic phenomena is crucial for helicopter pilots to effectively control and maneuver their aircraft. Two critical angles, angle of incidence and angle of attack, play crucial roles in enabling a rotor disc to generate the necessary lift for helicopter flight. The angle of incidence, often referred to as blade pitch angle, represents the mechanical angle between the chord line of a main or tail rotor blade and its rotor disc. It is a mechanical parameter and, in the absence of induced flow, coincides with the angle of attack. However, changes in induced flow, upflow, or airspeed can modify the relative wind, causing a difference between the angle of incidence and angle of attack. Collective input and cyclic feathering can alter the angle of incidence, subsequently affecting the angle of attack and lift produced by the airfoil. On the other hand, the angle of attack is an aerodynamic angle, representing the angle between the airfoil chord line and the resultant relative wind. Angles of attack is not easy to measure directly but plays a significant role in lift generation. Increasing the angles of attack diverts air over a greater distance, resulting in increased air velocity and lift. However, beyond a certain point, a further increase in angles of attack can lead to turbulent airflow, increased drag, and eventually a stall, causing a rapid decrease in lift. Pilots indirectly control angles of attack through flight control inputs, with collective and cyclic feathering being instrumental in making these adjustments. Collective feathering changes the angle of incidence uniformly on all rotor blades simultaneously, influencing the overall lift of the rotor disc. Cyclic feathering, on the other hand, changes the blade's angles of attack differentially around the rotor disc, creating differential lift. It is employed to control the rotor disc's attitude, counteracting rearward tilt and addressing dissymmetry of lift. Other factors, such as changes in airspeed, rate of climb or descent, and automatic responses like flapping in the rotor system, contribute to variations in angles of attack. Flapping. The up and down movement of rotor blades compensates for changes in lift due to velocity variations or cyclic feathering, playing a crucial role in addressing dissymmetry of lift. Pilots manipulate angles of attack through pitch angle adjustments, influencing lift production in the rotor disc. In powered flight, which includes hovering, vertical ascent, forward motion, sideward movement, or rearward travel, the combined lift and thrust forces generated by a rotor act perpendicular to the rotor disc. This configuration allows the rotor to effectively support the helicopter in the air and control its directional movement. The rotor's ability to produce lift and thrust in a coordinated manner is essential for the helicopter's stability and control during various flight maneuvers. The perpendicular orientation of these forces ensures that the helicopter can achieve and maintain the desired altitude and direction as dictated by the pilot's inputs and flight conditions. Hovering is a challenging aspect of helicopter flight due to the generation of gusty air by the helicopter's own rotor, creating constant corrections by the pilot to maintain the desired position. Control inputs during hovering are simplified, with the cyclic used for horizontal plane adjustments, the throttle controlling revolutions per minute or RPM, the collective maintaining altitude, and the pedals controlling nose direction. The interaction of these controls requires constant correction, making hovering demanding. In a hover, lift overcomes gravity and weight, while thrust allows horizontal movement. The pilot manipulates thrust using the cyclic to induce travel or compensate for wind. In a no-wind condition, opposing forces like lift, thrust, drag, and weight are in balance, resulting in a stationary hover. Adjusting the angle of incidence through the collective controls the amount of lift to maintain hovering height, with excess lift causing ascent and insufficient lift causing descent. Drag during hovering is mainly induced drag from blade lift production, along with profile and parasite drag from non-lift producing surfaces. Torque induced by the engine turning the main rotor requires an anti-torque rotor, typically a tail rotor, to counteract the turning tendency. Translating tendency. A lateral drift during hovering is counteracted through design features or control adjustments, ensuring a stable hover.